Welcome back. The time has come for me to fulfill an old promise. In this lesson, we are going to talk about variance problems, and I mentioned them quite a few times both in this course and in the beginner's course. We are going to dive really deep into what variance is, variance positions, compiler restrictions, and a few solutions. So back in our IDE, let's create a new Scala application under Part 5 type system. So create a new Scala class, let's call this Variance. Make it an object, and as before, extends app. And assuming another jungle-like class hierarchy, let's call this animal as a trait, and we have some classes. Let's say dog extends animal, not exactly a jungle, but still with animals. So we have a class dog, also a class cat, extends animal. And let's also have a class called crocodile, just for some variety. Okay, so it's really simple type hierarchy. Now, what is variance? Now, variance is the problem of quote-unquote inheritance. I'm putting this quote-unquote because it's actually the problem of type substitution of generics. So say, for example, I have a class called cage, which is parameterized with some type. Now, the question is, because, for example, cat extends animal, the question is, should a cage cat also, quote-unquote, inherit from cage animal? Now, the possible answers are yes. And this is called covariance. So if I declare a class called, let's call this cCage from covariant, and if I put in a little plus sign here, then this will be covariant in the sense that if I declare a val cage or cCage as a cCage of animal, I can say that this is a new cCage of cat, because cat extends animal. And this intuitively makes sense because I'm replacing a general cage of animals with a specific cage of cat. All right, so this is one possible answer. Another possible answer is no, and this is called invariance. So when I say class cage with a type parameter t, let's redefine it here as iCage, I for invariant, then the types are completely different. I cannot replace any type with cage with any other type of cage. So if I say val iCage, which is a cCage of animal, equals new iCage, of course iCage inside, with cat, then this is wrong. It's as if I said val x of type int equals hello world. All right, this is as bad for the compiler, okay? So I'm just going to comment these out. And the third possible answer to should a cage of cat inherit from a cage of animal is hell no, or even opposite. And this is called contravariance. And the way that we mention contravariance is by putting a minus sign near the type parameter. So if I declare a contra cage with a minus t, then this is a contravariant cage. And the type substitution works in the opposite sense. So if I say val xCage, which is of type xCage with cat, equals new xCage with animal, then this is a valid substitution. Now, you may be wondering, why on earth would you want that? So, although counterintuitive, this can also make sense. I'm replacing a specific cage of cats with a general cage of animals. Rationale being that if the value on the right-hand side here can contain any animal, it can also contain a cat, so it's a good replacement. Okay, so with this kind of background, let's define some various types of animal cages, this time with an animal inside. So, as a prototype, I'm going to define an invariant cage of type t with an animal of type t inside. Okay, this is invariant. So Let's talk about covariance and covariant positions. Let me show you what I mean. So if I declare a class called covariant cage, which is covariant in the type T, and this holds a val animal inside, then we say that the generic type of vals of fields are in a covariant position. What this means is that in this place, in this position, the compiler accepts a field declared with a covariant type. Covariant positions or covariant places, like field declarations for a class, also accept invariant types. So if I make this a val, this is also compilable. So if I compile this, the compiler will be happy. Now, if I put a contravariant type in a covariant position, such as in this place, if I declare a class contravariant cage with a -t here, and I'm putting the val animal here of type T, then if I compile this, the compiler will complain saying contravariant type T, because it's a negative sign here, occurs in covariant position in type T for animal. Now, the reason is that if the compiler was able to pass this code, then I would be able to write something like val cat cage, which is of type cage or contravariant cage, or x cage of cat, all right, equals new x cage of animal with something that extends animal, such as new crocodile. Because it's an animal, right? I'm declaring an x cage of animal, so I can put in an animal inside. A crocodile is an animal, so what's the problem? Well, the problem is that I originally wanted a more specific cage, and you're filling it with some other kind of animal. Well, that's a problem. A similar logic applies for vars, var fields. So if I declare a class, say covariant variable cage, all right, so this is covariant, and it takes a var animal of type T, then this will also not compile, and the compiler says covariant type T, because it's a plus, occurs in, this time it's a contravariant position. Let's recompile this so you can see the full message. So covariant type T occurs in contravariant position in type T for variable animal. So the types of vars here are in contravariant position. Because if the compiler somehow passed this code, then I would be able to write something like, this is covariant, right? So if I said val c cage, which is a covariant cage with animal, equals new c cage of cat with a new cat, that would be fine. But since this c cage is a covariant cage of animal, then I could put in another animal inside. So c cage dot animal, because it's a field, I could put in a new crocodile. And that, in theory, would be fine if the compiler passed this code, because this is a c cage animal, so I can put in an animal inside. What's the problem? Well, it's a problem, because the instantiation might be something more specific, and I won't be able to pass in another animal inside. All right? So the types for vars here are called in contravariant position. But the types of vars here are also in covariant position, because if I say class contravariant variable cage with a negative sign for T, and if I put in another var here, type T, then this code will also not compile. Saying contravariant type T, which is negative, occurs in covariant position in type T of variable animal. So the variable here is also in covariant position. For the same reason as we saw with values earlier. So this same logic applies to variables as well. We can instantiate a cage animal as a cage cat with a new crocodile inside, which is totally wrong. So because variables are in covariant and contravariant position, the only acceptable type for a variable field is invariant. So if we say class invariant variable cage with type t and put in a var animal inside of type t, this is okay. Okay, so the compiler is now happy. So as we saw, covariant and contravariant positions are basically some compiler restrictions. Let's see a few more examples. Let's run through a classical example of collections. So a cage is our little small collection for an animal. So if I declare a small trait, let's say another covariant cage. I'm writing different examples here so that we may isolate our situations. So if this another covariant cage had a small method called add animal. This is a classical example of a collection that is covariant, and we want to add an element. This is super innocent. So we want to add an animal of type t. Now, as we see, the compiler underlines this code with red, saying covariant type t, because this is a plus, occurs in contravariant position. So method arguments are in contravariant position. And this code does not compile because otherwise I would be able to write something like, say for example, I created a covariant cage. Let's say val c cage equals, which is of type covariant cage of animal equals new covariant cage of dog. Okay, and I would say covariant cage, because this is a cage of animal, add new cat. We don't want cats and dogs in the same place, so the compiler forbids us from adding methods with covariant types. But otherwise, I would be able to say, if I wrote a contravariant collection, so say add class another contravariant cage of type minus t, and declare a method called add animal, which receives a parameter of type t. And this just returns like true or something. This is fine. So if I compile this, this runs well. Because if I say val, say another contravariant cage, which is declared as another contravariant cage of cat, instantiated as another contravariant cage of animal, then I cannot say acc.addAnimal new dog, because this is a contravariant cage of cat. So it must receive an argument of type cat or below. So if we declare a cat here, then this is fine. And if we also define a class called kitty, extends cat, then acc.addAnimal would also work for a new kitty. Now, this is a painful problem because we often want to create covariant collections and then get sad because we can't add elements to them. So the way that we would solve that would be to say, for example, if we wrote a class called myList, which is covariant in its type A, and we want to add a method called add, which adds an element of type A and wants to return another myList A, then the compiler currently complains that the element is in a contravariant position, but we can hack the compiler by saying that this add element receives a type parameter B, which is a super type of A, and instead of adding an element of type A, it adds an element of type B, and at the end it returns an myList of B. So this is basically widening the type. Let's just return a new myList B so that the compiler is happy that we supply some implementation. We don't really care about the actual implementation, we only care about the method signature. Now, this is what we want, because if we create an empty list, for example, which is a new myList of very specific, of type kitty, okay? Empty list with an L, okay? Now, if we say val animals equals empty list dot add new kitty, then this is fine because a kitty is either the type kitty or a supertype, so the animals list is still a list of kitty. But if we want to add, let's say, more animals, equals animals.add a new cat. This is the kind of scenario that the compiler wants to avoid if we don't declare this little type parameter here. But now the compiler is happy because cat is a supertype of kitty, so at the end, the compiler will return a new mylist of that type, which in this case is a list of cats. As you see, this is a mylist of cats. And we can also supply some kind of other animals. So if we say even more animals equals more animals add new dog, this would be disastrous if we hadn't added the type parameter here. But now the compiler is happy because a dog is an animal. This is the next lowest ancestor of both cat and dog, so the compiler will widen the return type of even more animals to animal. Our goal here is that at all times we want to keep the property that all the elements in a list have a common type. That's the very reason we're doing typed collections, right? So if we say something is a list of cats, well, it can only contain cats and nothing else. But when we add a dog or a crocodile to it, then the property will break, and the compiler is then forced to widen the type to keep that property true. Alright, so we talked about how method arguments are in contravariant position. I'm going to write that again so it's very, very clear, because it's going to bite you at almost any point when you want to create generic APIs. So method arguments are in contravariant position. Let's talk about method return types. And I'm going to illustrate that by declaring a small class called petshop with a contravariant return type. So a petshop of things that are contravariant, okay? And let's imagine that we have a method called, say, get, and this receives some kind of parameter. For example, is it a puppy, which is of type Boolean. And the rest returns a t, which is the kind of animal that we want to return. But the compiler says, nope, contravariant type t, because it's a minus, occurs in covariant position in type t of value get. So we have that method return types are in covariant position. So this guy right over here is a covariant position. That's because if the compiler somehow passed this code, I would be able to write something like, let's say I had a cat shop as a new pet shop of cats or animals. Okay, and the def get here would have returned me a cat in the form of an animal. So we had a pet shop of animal where the get method returned a cat. And if the compiler passed this code right over here, I would have been able to say val dog shop, which is of type pet shop of dogs. It's not a new pet shop of animal, but a cat shop, because this guy is a pet shop animal, so it's a proper replacement for a pet shop dog because the pet shop is contravariant. But of course, if I do dog shop dot get true, meaning I want a puppy, then this guy would give me an evil cat. So evil cats. So this is why the compiler doesn't allow us to use types here as a return type when they're contravariant, because the return types for method are in covariant position. The way that we would solve that would be to return a new type, which is a subtype of the original type t. So basically the opposite of the hack that we used earlier. So a solution to that would be to say def get of a type parameter s, for example, which is a subtype, not a supertype of t. And again, we could pass it the method arguments here with is it a puppy boolean, and instead of the return type t, we're going to return type s. And let's also supply some implementation in the form of an s. So let's say this method also receives a default animal, which is of type s, and just returns the default. Okay, we don't really care about the implementation, only that it has a value of type s. Now, if we have a value shop, which is of type pet shop dog, and in fact this is a pet shop animal, which the compiler allows because pet shop is contravariant. Now, even if I wanted to say val evil cat, which is shop.get true and a new cat, I wouldn't be able to do that, even though the IDE doesn't underline anything with red. If I recompile this, the compiler says inferred type arguments do not conform to methods type parameter bounds. So cat does not extend dog, so this call is illegal. Conversely, if I declare a small class called Terranova, which is a breed of dog, extends dog, and I said val, let's call this big furry, equals shop.get true and new Terranova, then this would be allowed. So running this would be fine. So, big rule. I'm going to write this here. Big rule. First, method arguments are in contravariant position, and return types, let's align this, are in covariant position. Now, if we inspect the function types that are readily available in Scala, say function 1, then taking a look at the source for Scala, the trait function 1, as with all the other function types, the function types are contravariant in their argument types, as you see this negative t1, and covariant in their return types. And this is the case for all the other function types. So if I search for function 3, for example, we see that all the arguments for function 3 are contravariant, and the return type is covariant to satisfy the compiler constraint that the arguments for methods are in contravariant position, so they only accept contravariant and invariant types. And the return type is in covariant position, so it accepts a covariant or an invariant type. So let's get back to our little source in Variance, and let's do some exercises. But in the next video,